Now, in Day 4, Part 2,
we're going to take a look at yet another dynamic programming example. This one is called the longest increasing subsequence. And let me describe the problem here. So we have a sequence of n values, and we'll just label these from 1 through n, v1, v2, etc., up through vn. We're interested in finding increasing subsequences of these values. So an increasing subsequence is a sequence of these values where the subscripts of these values are in increasing order, although there may be gaps in between the subscripts. That is, 1 is going to be less than or equal to the subscript of the first value, which in turn is going to be less than the subscript of the second value in the increasing subsequence, blah, 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 which in turn is going to be less than the final subscript in the sequence of values, and that in turn has to be less than or n. So this is a sequence in which these J1, J2, Jk are some subsequence of the sequence 1, 2, 3, 4, 5, comma, n. Also, in this increasing subsequence, for each pair of values, the left-hand value has to be less than the right-hand value. Okay, all the way along. Well, we're interested in looking for the longest increasing subsequence within this original sequence, and so what that means is that we're looking for the longest one. I guess it's sort of self-defining what that means. All right, so let's imagine that we've got this sequence here, 5, 12, 2, 7, 1, 8, 13, 2. An increasing subsequence is any subsequence within this original sequence in which all of the values are increasing. Okay, so 5, 12 would be a trivial increasing subsequence. 5, 7, 8 would be another one. 7, 8, 13 would be another one, and so on. Now, the longest increasing subsequence, if we write down all of the possible subsequences in here where the values are progressively larger as we go through the sequence, we'll find out that the longest increasing substance we can get out of this is 4 long. But it's not unique. There are actually 2 different increasing subsequences that are 4 values long. We can either have 5, 7, 8, 13. That's one 4-value long increasing subsequence. Another one is 2, 7, 8, 13. And those are the only 2 that we can find in this sequence. Obviously, the longer your sequences get, the harder it is, just by brute force, to identify all of the longest increasing subsequences that there are. Okay, so let's take a look at how we can, so let's formally state the problem here. And it might be stated in a couple of different ways. One might be to find a longest increasing subsequence. Okay, you're not typically asked to find all of them, but you're asked to find one of them. Or you might simply be asked to find the length of the longest increasing subsequence without identifying a specific example of a longest increasing subsequence. Okay, so in the recursive formulation of this, we're trying to find the longest increasing subsequence, or the so-called LIS of the sequence of values. And we break that down in kind of the usual way. We consider the case where v sub n, the last item in the sequence, is in the longest increasing subsequence, or where v sub n is not in the longest increasing subsequence. Okay, so for the case where v sub n is in the LIS, then the problem breaks down to finding the longest increasing the longest increasing subsequence of the prior values but only those where the value is less than the final value, and then append the final value to that longest increasing subsequence. All right, so what do we mean by this such that clause here? Well, let's suppose that v sub n, the final value, is a 10. If that 10 is in the longest increasing subsequence, then because of the definition of what an increasing sequence is, all of the values prior to 10, all of the values prior to v sub n, which has a value of 10, must be less than 10. Okay, so if we have values that are greater than or equal to 10, we just throw those away, and we only consider the ones that are less than 10. Now, on the other hand, if the final value is not in the longest increasing subsequence, then we simply have the problem of finding the longest increasing subsequence in all of the prior values without any constraint. And we do have a stopping condition, because if the sequence only has a single value in it, then necessarily that is the longest increasing subsequence, that one item, that one value all by itself. All right, so the naive approach to this, unfortunately, blows up in exponential time, as we're more or less used to. Okay. So what we're going to do to memoize this, to create a dynamic programming solution, is just create a one-dimensional array to keep track of the lengths of longest increasing subsequences that end at a particular index. Okay, now as I said, if we only have one value in our sequence, then the length of the longest increasing subsequences has got to be 1. If we have two values in our sequence, then the longest increasing subsequence can only be 1 or 2. And basically that depends on whether v1 is greater than v2 or v1 is less than v2. If v1 is less than v2, then the longest subsequence of these two items is 2. But if v1 is greater than or equal to v2, then the longest subsequence is 1. And we continue following that with that same kind of logic to fill out all the rest of these values here. All right, so initially we're going to fill in all of the lengths in this lengths array with the value 1. Because at worst, even if every single one of the values in this sequence that we start with is equal to each other, at worst, each one of these things is going to be the beginning of a subsequence that is at least one value long. Okay, so if all of these values are 12, then this first one, just consisting of this first 12, is 1 long, and this second one, consisting of the second 12, is 1 long, and so on. So we're going to fill that in as our initial condition, or as our initial setup. Then, as we increase our subscript k, stepping through progressively longer portions of our original sequence, it might or might not be that the next value, v sub k, might be a continuation of some prior sequence. If we discover that v sub k is a continuation of a prior sequence, then the length of that subsequence, including v sub k, has to be 1 plus whatever the length of the prior subsequence was. Otherwise, it's just going to be 1. Okay, so for each value of k, let's start with k equal to 2, we're going to use another loop counting up to but not including k, and we're going to compare each of those values prior to v sub k to see whether it's less than v sub k or not. If it is less than v sub k, then that means that the length of the subsequence, including k, is going to be the maximum of the length that we already know about for k, or 1 plus the length of j, okay? Because however long j is, that plus 1 is going to be the... Sorry, let me say this again. However long length sub j is, that plus 1 has to be the minimum length that the values up to j plus vk itself is going to be. So that's going to be 1 plus the length of j. Now, once we have turned the handle and gone through all of these increasing values of k from 2 up to n, then if we look back through this lengths array, whatever the maximum value of the lengths array is, that's going to be the length of the maximum increasing subsequence. Okay, so let's walk through this step by step. So in this example, starting on slide 8, we're using the same sequence of 8 integer values that we looked at the beginning of this lecture, with our initialization that the lengths array is filled in with values of 1 for 1 value wide subsequences. And now we're going to set k to 2. Okay, k is going from 2 up to and including n. And as we change the value of 2, moving forward through this array, we're going to have an inner loop that's counting from I up to but not including, sorry, counting from 1 up to but not including k, and doing this comparison. All right, so k is 2, j is 1, and we ask whether v sub j, which is v sub 1, which is 5, how does that relate to v sub 2, that is v sub k? Well, 5 is less than 12. Consequently, when we execute this assignment statement here, we're changing lengths sub 2, this value, to be the maximum either of its original value, which was 1, or 1 plus length sub j. So in other words, that's the maximum of 1 or 1 plus 1. And of course that's 2. So we modify that value, length sub 2, to be 2. This is off by 1 if we're thinking about this in terms of Python code, because of course in Python code our array indexes are going to run from 0 up to n minus 1. But in this mathematical formulation, we're using indexes of 1 through n. So does that make sense? Well, yes, it does, because 5 was a 1-value sequence, 12 we initialized as a 1-value sequence, but now we've discovered that 12 is greater than 5, and so we have a two-value sequence, including the 5 and the 12. Onward ho. All right, so now we're going to change k to 3. So we've moved k forward. Consequently, the value v sub k, v sub k is this 2, which I seem to be unable to highlight. And we start out over again with j starting from 1. And we discover that 5 is not less than 2. So we don't change the value of length sub 2. On the other hand, with j set to 2, we discover that, and then likewise, I should say, with j set to 2, we discover that 12 is greater than or equal to 2. So again, we don't change length sub k. And that's it. Now k would hit, I'm sorry, now j would hit 3, but k is equal to 3, so we have to go on to the next value of k. In other words, we did not change this 1 to anything else. Onward ho. Now we've bumped k up to 4, and we have to step j from 1, 2, and 3. Well, the value of v sub k is 7, and if we have j equals 1, we discover that 5 is less than 7. Consequently, we have to modify length sub 4 to be the maximum of either 1, which is its original value, or 1 plus 1, which is the value for 5. The value for v sub 1 is 5, and that gets us a 2. All right, this next value is 12. All right, so if j is 2, the value is 12. 12 is greater than or equal to 7, so we don't change the lengths array. And then in the third step, where j is 3, 2 is less than 7. So this might, at first, look frightening, because goodness, if 2 is less than 7, doesn't that mean that we need to increment that counter? But on the other hand, 2 is also less than 5, so isn't that going to screw us up? No, because what we're doing here is we're computing the max of the current value of length sub 4, which is already 2, or 1 plus 1, which would also get us to 2. So what this is saying is that at 7, the maximum longest increasing subsequence that we have is 2 long. And either 5, 7 is such a sequence, or 2, 7 is such a sequence. So those are both increasing subsequences up to and including the 7, but they are each of length 2. Okay? Now, for k set to 5, okay, we increment k again, and now v sub k is 1, and 1 is less than everything to its left, so this value here is going to remain, in other words, length sub 5, the longest increasing subsequence length for 1 itself is going to remain at 1. Okay, and then I don't think I'm going to step through, value by value these remaining things. It's just quite mechanical. We discover that when we get up to v sub 6, which has a value of 8, that we increment the sequence length to 2 initially, all right, because 5 is less than 8. And then when j comes up to 4, we increment that length sub k, to 3. Okay, so because 5 is, well, this one's over here. So because 5 is less than 8, we increase this from 1 to 2. And then because 7 is also less than 8, we modify length sub 6 to the maximum of 2, which is the value that was there, or 2 plus 1, which is this value of 7 plus 1, and so that gets us to the 3. Okay? And if we look back at this, which we don't have to do, but if we look back at this, we would discover that if we're ending at 8, then 5, 7, 8 is an increasing subsequence that's 3 long. Similarly, 278 is another subsequence that's 3 long. Both of the maximum length increasing subsequences are 3 long at that point. And then, without flogging things to death, we discovered that when we get up to 13 with k equal to 7, that the maximum increasing subsequence length we get there is a 4. And when we finally get out to 2, the maximum increasing subsequence length there is just a 2, all right? Because the only subsequence we have that ends with this 2 that is increasing consists of this, whoops, can't highlight, all right, consists of this 1 and this 2. Alrighty, so we look back and discovered that the length of the longest increasing subsequence is 4. That's simply the highest value in the lengths array. And we can find an example of a longest increasing subsequence ending with 13 and discover that 27813 is one such example. If we go way back to the outline of the algorithm, we've got for k going from 2 up to n, and for j going from 1 up to k minus 1. So we've got nested loops, which leads us to a performance of n squared. Alrighty, so that one is not so bad.